Edexcel Further Maths Core Pure 1 Specimen Paper, Question 4. This question kicks off by defining a function, which is a piecewise defined function. In other words, separate pieces are defined separately. So we've got this curve while x is between 0 and 3, and from 3 upwards, we have this curve. Now, it's not necessary for this particular question to be able to sketch or visualize these, although you might find it helpful. The important thing is that we check our assumptions and we are aware of the general behavior of the curves insofar as we need to know. They're looking for the area between the curve and the positive x-axis. Technically, they've given us the value of the area, and we're going to need to work backwards to do stuff in terms of k to find what value of k would make the area this. So it looks like these two have been scaled, and there's one interesting approach to this. Given that they've both been scaled in the same way, you could consider the function f of x over k, which is basically a scaled down version of f of x. And then you could compute the precise area for the x over x squared add 6 and 1 over x squared minus 4 curve. You could even check your answer to that with the calculator to make sure you're doing things right all the way along. And then at the end, you could say, well, that's the f of x over k, and if we know that the actual area is 1 over 4, we can scale things and find the appropriate value of k that will make that work. Depending on where k appears, however, that's not always going to be as straightforward as that. So we're going to work through this, not making any assumptions about how nice it is that k appears as a factor of both. We're just going to work through as we ordinarily would with a question like this. And the first thing to notice is that we don't have the limits. It just says the area between the curve and the positive x-axis. We know for a start that we don't need to worry about negative values of x because this curve is only defined for non-negative values. It's defined for 0 and upwards. But we do need to think about where the curve crosses the x-axis, because presumably that's how we're going to find the limits that we're going to use. So we need to solve f of x equals 0. When does it cross the x-axis? That will be the points when the output is 0, when the y-coordinate is 0. But when you've got a piecewise function like this, you have to consider two different possibilities. Maybe it crosses the x-axis between 0 and 3, in which case kx over x squared add 6 is 0. Or perhaps it crosses somewhere else, at a point that's 3 or greater, in which case k over x squared minus 4 will be 0. We can consider each of these in turn. We'll start with this one. It looks like x has to be 0. It's quite nice here. We found a value that doesn't depend on k, so we don't have to have k's in the limit, at least. K is going to appear within the integral, but not in the limits that we put the integral between. This is the only solution here because this is a fraction. The only way a fraction can be equal to 0 is if the numerator is 0. Another way to look at it is you could multiply top and bottom. You could multiply both sides of the equation by x squared add 6, and that would make the denominator disappear from the left-hand side. It would also disappear from the right because the right's got a 0 on it, and you're left with kx equals 0. What about the other one, k over x squared minus 4? Well, by the same token, this can only be 0 if k is 0. But it tells us in the question k is a positive constant. So the curve has been scaled up by a factor of k. It's equal to 1 over ln of something. That's what we're going to prove later, but we can assume for now the thing we've been told, k is a positive constant. If k is a positive constant, this curve is never 0. There are no values of x for which this is 0. So how is it that we can be asked to compute the area between the curve and the positive x-axis if it only crosses the x-axis once? Well, for that, we need to think about the long-term behavior of this part of the function. As x increases without limit, what happens to k over x squared minus 4? Well, x squared gets bigger and bigger pretty quickly, and even if you take away 4, it's still going to continue to get bigger and bigger and bigger. K is fixed. K is just a constant of some sort, so you have a constant divided by an ever larger number. So what we should notice here is that k over x squared minus 4 is approaching 0 as x increases without limit. In other words, as x approaches infinity, positive infinity. So even if we can't visualize this curve, we know that it only ever crosses the axis once, it crosses at the origin, but we know that once we get beyond the switch over between the two parts of the piecewise function, the curve is going to approach the x-axis once more. It'll get asymptotically close to it as time goes by, or as x increases. It might be worth checking just to make sure that the curve before doesn't have any weird asymptotes, but you can see that x squared add 6 is never going to be negative because x squared is never lower than 0, which means that kx over x squared add 6 is always going to give an answer. It's not undefined anywhere. So there are no asymptotes for that first section. And there's only one crossing point when x is 0, which means it's going to be above the axis for all the values of x between 0 and 3. Remember, x is positive. The denominator is always positive when x is anything because it's going to be x squared add 6, so it's always at least 6. The numerator is positive provided x is positive because we already know that k is positive. So no matter what this curve does, we already have some sense that it's going to be something which is crossing at the origin and positive. We don't even know at the moment whether it changes suddenly at the cutoff point, but it's going to approach the x-axis once more as time goes by. So even if your diagram is as rubbish as this one, you've already got a sense of what's happening, and we know that the curve begins at the origin and eventually tends towards the x-axis once more. We can double check if you're curious what happens when x is 3. We get k times 3 over 15, so k over 5, but that's subbing it into the top one. So that's not technically a value that the function ever takes because we only ever get numbers very close to 3. But it's still a useful value because it tells us what this function is approaching as x approaches 3. For the next one, if you try subbing it in, we get k over 5, which is the same thing. In other words, this function picks up where this function leaves off. And our graph is more likely to look more continuous than the version I just drew. So if we know that it crosses at the origin, it's probably going to do something like this. It may be that the gradient changes quite dramatically. There's no rule that says the gradient has to be nice and continuous just because the function is continuous. But what we do know for sure is that it crosses at the origin and it approaches the origin once more at an asymptote as time goes by. So we can make use of that. We've got that picture in our heads that we can hold as we work through the rest of the question. And that means that this question is going to involve improper integrals. We want the total area under the curve, which effectively means we need to find the integral between 0 and infinity of f of x. And that needs to be broken apart into two separate pieces. That's going to be equivalent to the integral between 0 and 3 of the first part, that's the kx over x squared adds 6, and then we're also going to need to add on the integral between 3 and infinity of the other part, k over x squared minus 4. And for simplicity, I think it makes sense to break these into two separate pieces. So let's have names for them. This one is going to be integral I, and this one can be j. And we're interested in the total area, which for the sake of argument, we'll call A. So A is simply I plus j. And once we've worked out the values of I and j, we can add them together. This is a very quick thing to do in terms of notation, but it's really helpful when it comes to combining things when you're in a bit of a muddle in the middle of a question. So let's start with the first one. We'll compute the value of this first integral I. We go from 0 to 3, and the first thing to notice here is this particular integral can be dealt with using inspection. You might not spot it immediately, it's a little trickier because of the k, But whenever you're dealing with an integral involving a fraction, you want to ask yourself, first of all, is there something quick I can do? Is there an easy thing? Perhaps you would think of this one as a substitution. We can have u equals x squared add 6, and then du by dx would be 2x, and the x from the du by dx would cancel with the x in the numerator. Possibly a nicer way to do it would be to pull out the k, leave yourself with an integral that is a little less confusing to look at, and you might spot the trick that I'm alluding to at this point. The trick is the log trick, where the numerator is the same as the derivative of the denominator. So if the top is the derivative of the bottom, then all we need to do is to integrate is write down ln of the bottom. The top is not the derivative of the bottom, but it very nearly is. X squared add 6 differentiates to give 2x. And I'm allowed to put a 2 on the top there, as long as I also put a 2 on the bottom somewhere else. Remember, k is a constant, which is why I'm allowed to safely pull it outside the integral sign. You don't have to pull it out entirely if you don't want, but I think it makes life a little bit easier here. So I'm going to leave k over 2 outside, and I'm going to integrate 2x over x squared add 6. That gives me ln of x squared add 6. Good convention to use the modulus signs, but of course x squared add 6 is always positive, so it's not crucial here. We need to sub in our limits, which are 0 and 3. Nothing undefined or weird here, so everything should be fine. I'll have k over 2 multiplied by, and it's going to be ln of 3 squared add 6, which is ln of 15, minus ln of 0 squared add 6, which is ln of 6. And the simplest way to write ln of 15 minus ln 6 is going to be ln of 15 over 6, because we can use our log laws. And of course, 15 over 6 simplifies down. We can divide top and bottom by 3, and we get ln of 5 over 2. So that's our first section. We've got the integral, if you like, of this piece here. Call that I. We still need to look for this section here, which we're going to call J. So now we've got one part, we just need to go looking for the next part. This is where life gets a little more complicated because, remember, we have an improper integral. It's improper specifically in this case because it has an undefined limit. They're the easiest ones to spot. Instead of a hole somewhere in the function that you're integrating, or some weird limiting thing happening for one of your limits or somewhere in between, we just have a limit of infinity. And the simplest way to think of this is to find the limit of the integral for some other value. So I might use t. The integral from 3 to t of k over x squared minus 4. I'm also going to rewrite this as x minus 2x plus 2, for reasons that will become clear once you've had a think about the integral. But now, if I can compute this integral between 3 and t, I can then go back and find the limit as t tends to infinity. And I'm going to do that separately. So let q equal this integral. And then I'm going to work this out without worrying about writing limit every single time, so that what I'm writing is valid, but it's not too tedious. How do I sort this out? Well, I'm going to want partial fractions for this one. The numerator cannot be scaled to become the derivative of the denominator because x squared minus 4 differentiates to give 2x. K is not a multiple of 2x. But what we can do, as you've seen, is factorize. This is the nice difference of two squares. So we can pull this apart into two factors. And using partial fractions, we can say that k over x minus 2x plus 2 has to be equivalent to a over x minus 2 and b over x plus 2. One thing you might do to make this a little easier still is to pull the k out, leave this as a 1, and that makes your partial fractions problem a bit simpler. So it's not essential. You can find the values of a and b in terms of k, but you might find it a bit easier to simplify the problem down for yourself before you do these messy bits. Now you probably have your own preferred approach for this, but I'm going to focus on the denominator from the right hand side, the denominator from the left, and I'm going to notice that at x equals minus 2, we get a times nothing and b times minus 4. So b is going to be minus a quarter. Similarly, when x is 2, we'll have a times 4 plus nothing equals 1. So a is positive a quarter. If you do this by comparing coefficients, you'd be saying ax and bx is equivalent to no x's. So a add b is nothing. And then a times 2 and b times minus 2 gives 1. So a minus b has to be a half. Either way, however you do it, you should come out with the same values. And we can now say that q, our integral that we're trying to deal with, is not simply this, but can be written as a quarter over x minus 2 minus a quarter over x plus 2. And if that looks clunky to you, well, I definitely agree. I'm going to pull out that quarter from both of those and leave it as k over 4 in front. This will make it less likely that I mess something up as I do the next steps. So I've got k over 4, and I can now integrate directly. This becomes a fairly straightforward process because each of those is the reciprocal of a linear term, so it's just going to be logs involved here. ln of x minus 2, ln of x plus 2. The derivative of x plus 2 and the derivative of x minus 2, they're both 1, so there's nothing else complicated we need to do here. Essentially, you could say the top is the derivative of the bottom, so we're using the same trick we had before. We now need to apply the limits. The limits in this case, remember, were 3 and t, and we're going to worry about what happens as t gets very, very large later. We're pushing that problem to one side for the time being. Now, to make our life a bit simpler here, you might want to combine these logs initially, but it's kind of up to you. You're better off writing something that's clear and makes sense to you than trying to do too much all at once. So we'll have ln of t minus 2 minus ln of t plus 2. And that's in the first of the two brackets. And then we're taking away ln of 3 minus 2 minus ln of 3 plus 2. And that should all simplify down. K over 4 times, well, ln1 will disappear completely, so that'll be gone because ln1 is 0. ln of something, take away ln of something else, can be written as ln of the first something divided by the second something. And then we're still taking away negative ln5, so we're adding ln5, and we can incorporate that as well if we like by multiplying by 5. There we go. That looks relatively nice. Get rid of our brackets, make things look a bit nicer. This is q, and to find j, I need the limit as t tends to 0 of q. As t tends to infinity. So what happens as t tends to infinity? Well, for this, it might look a little confusing. 5 times infinity minus 10, nothing nice jumps out then. But there's a more efficient way of writing this, which you will hopefully remember. You can divide the top and the bottom of the entire fraction by that leading term, in this case by t, sometimes by t squared or equivalent. And that means that if you want t to tend to infinity, you've now reduced this problem to one where you have reciprocals of t, and the reciprocal of t, if t tends to infinity, will tend to 0. 10 over t will shrink towards 0 as t tends to infinity. So we just have k over 4 times ln of 5, take away nothing, over 1 plus nothing. There it is, just ln 5. Now that was j. We already found I. This is why it's so helpful to label things. We've got the value of I, we've got the value of j. We know that to get the area, we would need to add the 2. So the area is I plus j, which is going to be this, k over 2 ln of 5 over 2 plus k over 4 ln of 5. I'm going to write that slightly more simply. Pull out a factor of k over 4. I have 2 ln 5 over 2 plus ln 5. Don't waste too long doing all your simplifying steps here, but bear in mind that because we know where we're going with this, there are some things that are worth doing. They've said that the area is a quarter, and we have to solve and find k. So writing this next expression as simply as we can will help us when we come to solve an equation where we say this equals a quarter, basically. So let's keep going a little bit and have k over 4 times. Now to combine those log terms, the easiest way is to start by combining this one, 2 lots of ln 5 over 2, we can bring the 2 inside, call it 5 over 2 squared. In other words, 25 over 4. And we still have the other log 5. And log 25 over 4 plus log 5 is going to give log of 25 over 4 multiplied by 5. So 125 over 4. That is a nice simple expression. Now we can say that since a equals a quarter, we have 1 quarter equals k over 4 times ln of 125 over 4. And this is encouragingly similar to the format they were asking for. They said it should be possible to write k as 1 over ln of something. And we've managed to write k as 1 over ln of 125 over 4. So let's double check the question, make sure we've answered what was asked. K equals 1 over ln a, where a is a constant to be determined. They're not giving us any clues about the value of a, but the fact that we have 1 over ln of something is a pretty good sign. So it looks like we found the value of k. And now to finish up here, if you have the time to do your verification, what do we do here? Well, we've got a value for k. The calculator doesn't have k as one of its numerical options, but to make our life easier, I'm going to type in 1 over ln of 125 over 4, and I'll give it a name. I'm going to label it as C, because that's what my son calls K. He's just learning. So now we've got it named C, we can refer to that. What I want to do next is actually compute the two areas that we're interested in. We can't do it in one go because we'd have to define our piecewise function. But what we can do is integrate. It'll be c, in this case, c times x divided by x squared plus 6. Integrate that between 0 and 3. And then I can also integrate c over x squared minus 4. And that one I'll integrate between 3 and infinity. Well, I can't put in infinity, and the calculator wouldn't know how to deal with it if I could. But I can type in a fairly large number, and that'll give me a pretty good approximation. It might take a beat because we're asking it to do essentially numerical integration. But here we're getting out a value of 0.2497. That's pretty close to a quarter. And if you want even more convincing, give it a more demanding problem. Tell it to go to 10,000 and see how long it takes it. We should find that the area comes out very close to a quarter and increasingly close as we increase our upper limit. But it should still be less than, because the further we go along, the closer we get, the higher we get, and the closer we get to the value we're asked for. So now we've not only solved the problem, but with an extra couple of minutes of verification time, we've convinced ourselves that the value we've got is, to all intents and purposes, as precise as it can be. The calculator can't tell any difference. So if we have made a mistake, it's going to be quite a small one. And it's unlikely in general that you've made a mistake and it has this little effect on the final answer. So that was question 4.